So this is Grace here from NRC. So the federal government runs the National Research Council in Ottawa, and they've got a building science division there where they test building materials. They do all kinds of neat stuff. Right now they've got 3 houses built on the campus already that they have the ability to test a crazy amount of things in it. And they're building a duplex right now that's going to be very radon specific for testing. So what Grace has got there, this was when they ran tests on this product here. This is a structural sub-slab insulation panel for new construction. It's now code approved, CCMC approved, to take the place of that clear gravel layer that I showed you in the code. What it does is it creates a much better airflow under the slab than the clear gravel does. This has got 70% void space under it, and it adds insulation value. So this would be a performance solution for new construction, and I would advocate that this be used over clear gravel all day long. And there's a couple reasons here. See, in this house here, or this building here rather, they've used radon guard underneath. There's a barrier membrane product here as well. This is an engineered vapor barrier. And we engineered this product to have a 0 radon diffusion coefficient. We got it to 0.007, and that was as low as we could get it. So it's a system. It's 10-foot by 150-foot rolls. You overlap the interior seam. There's a tape made out of the same material that seals the interior. At the perimeter, you roll it under itself, and there's a butyl tape that goes onto the footing, and then you pour your slab. Both of these products are CCMC approved, so they'd fall into the performance category of the code. If you use those, you do not have to use the clear gravel. So I'm not as familiar with gravel pricing on the island here, but in some markets, that product is actually cheaper than the clear gravel. And there's 2 drawbacks from the clear gravel, or 2 or 3 arguably. One is that we know from smoke testing we've done, when we put that pipe in and actively depressurize the slab by pulling air through the clear gravel, we're pulling air from under the footings outside the building. We've run smoke tests with that, so we know that occurs. And there's fine particulate that gets pulled through that gravel. So while day 1, your system is communicating throughout the whole slab and taking air from everywhere, by day 30, that's diminished somewhat. And by day 365, it's diminished more. So Health Canada released a survey in July 2016. They had mitigated 52 houses, aftermarket houses like you folks have just tested. They'd put in active slab depressurization, so they'd put a pipe in, cut a hole in the concrete, put a pipe in, sucked air through the gravel. And these were done by industry professionals. These were done properly. I know the guy that did them. He's the best mitigation guy in the country, or one of the best mitigation guys in the country. So 12 months later, they could get back into 40 of the 52 homes, and already 4 of the homes had elevated radon levels again because the communication had diminished under the slab. So we know that gravel thing is, while it's a solution, it's maybe not the best solution. And in Europe, incidentally, they don't use that gravel anymore. They use air handling and air changes, which I'll talk about shortly. So the other drawback with pulling air through the clear gravel, NRC presented a study in Belgium in July last year at the Indoor Air Quality Conference. They tested the cooling effect on the slab of pulling air through the gravel during the heating season. So they determined that the slab has a temperature drop of 2 degrees C every 4 weeks in the heating season. So in a colder climate where you've got a 5-month heating season, that's a 10 degrees C temperature drop in the slab. So it's an immense heat loss in the building. And in today's movement of energy efficiency, that's going the exact opposite direction. So with this panel here, you've got the insulation value as well. So it kind of makes more sense. You've got better airflow, better energy efficiency, just all around. Oh. So I mentioned a minute ago in Europe how they mitigate. They don't do this slab depressurization anymore. They've moved completely away from that. They use a device like this. This is an indoor air quality sensor that gets installed in a building, and it constantly monitors the air for radon levels. The way this works is it gets connected to the air handling system. So a room like this, beautiful old historic building, you're not going to break the floor and run pipes up through the middle of this. That's just not going to happen. And it's not going to be efficient because when this building was built, they weren't putting gravel under the slab. There would be clay or muck or something that doesn't communicate. So this would go into this room. It would get connected to the terminal strip on the rooftop air handling system. So if there's 5 zones, maybe there's 5 air handling units in this room, you'd put 5 of these devices in. When it measures a peak of 150 becquerels, it closes a circuit and turns on the air handling system on high-speed override, runs it for 20 minutes, so it changes the air in the building, and then it shuts down, unless it's still sensing a peak of 150. If it is, then it runs for another 20 minutes. And when this gets installed, the system is rebalanced, so when it comes off high-speed override, it lands on a slightly positive pressure, only a couple becquerels. And what that does is it's the same effect as depressurizing the slab, except for we've positively pressurized the room so that physics don't work. It doesn't work anymore. Something won't move from an area of low pressure into an area of high pressure. It will move from an area of high pressure into an area of low pressure. So if we positively pressurize the room, it stops the ingress of radon that was occurring at that point in time. And it's interesting, yesterday mentioned I was presenting to the Greater Vancouver Home Builders Association. There's a movement in the building community that sees houses going in the near future to being positively pressurized. And that'll have a huge impact on radon entering new houses if they do that. So what does all this cost? If you were a builder today in BC, and these are numbers that I worked with BC Housing on, the code is the prescriptive version of the code, putting the clear gravel in and running that 4-inch Sked 40 PVC pipe outside at time of construction, depending on where you are in the province, adds between $300 and $1,500 to the cost of a house. So you folks know what the value of a house is in BC these days. It's not a lot of money. If you went the performance route, radon guard and block here, the combination of these, you're looking at $600 to $1,500 more. If you went the Radostat route, it's $1,500 more, and that's really the $1,500 is the cost of this. So in a house, this would connect to the HRV or ERV in the house. That's the machine that changes the air in the new houses today. Some of you may have them, some of you may not have them. Great way to mitigate. They're super, super efficient. You don't need a lot of CFM. 150 CFM HRV is enough air volume to get the radon levels down. So here's kind of, a couple options. The subslab depressurization, right here from gravel. This is what it would look like if you test high. You'll end up with an inline radon fan. That radon fan runs 24/7. It's a sealed fan, certified sealed fan. One of the problems, the other problems I have with the BC code and the rough-in is it makes it simple for a homeowner to go online and buy a radon fan and install a system themselves. And it's not quite that simple. The professionals, when they install these systems, they core 3/4 inch holes or 1/2 inch holes across the entire field of the slab. They put manometers in them and they run a vacuum test to test the communication under the slab before they size the fan. And right now, I see builders out there putting fans in themselves. They're just buying them online. They have no idea what CFM to buy. And in this case, more CFM is not necessarily better. Sometimes it's better with only 60 CFM versus 150 CFM. So the Radostat, the Radostat here connected to the HRV, ERV, it eliminates all this calculation. So here's a bit of a case study. This was a building that was mitigated. It's actually a federal government building in Prince George. SNC Lavalin at that time was looking after the federal buildings. The The workers had asked the building be tested because there'd been a radon survey in Prince George, and it was determined that 40% of the houses had elevated levels of radon. So the federal workers got their union rep to come in and demand that the building be tested. And sure enough, the building came back at 1,432 becquerels, which is very, very high. So the federal government made a decision right with SNC Lavalin. They had a big meeting, said, we're going to run the air handling system 24/7, constantly change the air until we come up with a solution in here, because it wasn't practical. It was a 17,000 square foot building. You couldn't put depressurization points. You'd need 20 of them in there, and nobody could say with certainty what was below the slab, whether the communication would have been good. So SNC Lavalin came to us and said, what do you think? Will this work? So we went up and looked at the building, and it had 5 air handling units, 5 zones, and we said, yeah, this is going to work. So we put 5 of these in, tied them 1-to-1 to the air handling system. In the first month, they saved $3,250 in energy costs alone, just by piloting the system on demand with the Radostat. And we took the level from 1,432 down to 71 becquerels. So even the WHO would be happy at that point. So radon and water, I talked a little bit about that in residential wells before. And we don't generally see high levels of radon in city water. And the reason we don't is because the purification process that city water goes through is all about aeration. So they're constantly aerating the water, and that releases the radon from the water. We do see it in cities that have aquifers. Prince George, a lot of the water, the city water, is drawn from an aquifer that's quite high. I had an engineer come to me yesterday from Nelson, BC, and there's a fairly new development up there that's drawing their water from an aquifer, and the water's got very high uranium content. So for us, that's a red flag. If it's got lots of uranium, it's going to have radon in it. And the houses, they're just testing the houses now, and the early results are in the 10,000 becquerel range, that's very, very, very dangerous, needless to say. So we have engineered a system to take the radon out of residential well water. And the way this system works is it goes right down the casing, so it's done outside the house. Traditionally, all the other systems on the marketplace for taking radon out of residential well water involve putting a big cistern in the basement, sealing that cistern, and then venting it outside. So it takes up a lot of space, it makes noise, you run the risk of a leak. If you ever have a leak in the house, the radon's getting into the house that you're trying to get out of the water. So for us, it made sense to look at a way to do it inside the well. And we developed this system, as I say, that we take the head off the casing, we insert piping all the way to the bottom. There's an active length that's 10 feet or 20 feet long, depending on the depth of the well. And we mount a driver box right on the head of the casing. And essentially what we're doing is introducing air into our system. It drives the active component, which creates a hydrodynamic pressure, draws the water from the bottom of the well up, and it gets aerated here and releases the radon outside the house at the point of the well. And interestingly enough, again, we were really working on radon, but this system works for sulfur and a few other things too. But if you weren't targeting radon, there's cheaper ways to get the other things out. But if you have a radon problem, it does work for the other things as well. So there's probably no architects or engineers in here, but I had this slide in my presentation. These products are, because we work with the building community so much, they're in what's called the Sikh Library in the Revit software and AutoCAD software. So what that means is, if you're in the process of building a new house and you've hired an architect, that architect is 90% sure he's using Revit or AutoCAD as software as design. He can just go in and pull these products and engineer them right into your house. So the higher the concentration in a dwelling, the sooner remediation action should be taken. That's a Health Canada position, and they actually say in the booklet you've got there that if you're between 200 and 400, you should mitigate within 2 years. And they are the only organization in the world that gives you a time frame. Everybody else says, if it's high, fix it now. And I've talked to the folks at Health Canada about it, and their position kind of is, you know, it was an economic decision. They didn't want to burden the population with the cost of mitigation. But, you know, the reality is that, you know, some of you will have a high level, and a mitigation professional, depending on the house and the type of house and the job they have to do, they're going to charge you somewhere between $1,800 and $4,500 to fix the problem, in all likelihood. So it's not a mountain of money. It's not insurmountable, especially in today's value of housing.